Welcome to Accelerating Your VR Applications with VRWorks, presented by NVIDIA, with Dave Weinstein, Director of Professional VR, NVIDIA.
Hello, good afternoon. I'm Dave Weinstein, Director of Enterprise VR at NVIDIA, and happy to be here today. So today, I'm going to be talking about VRWorks, which is our SDK for accelerating VR. But before we get into that, I want to talk a little bit about VR in general and sort of motivate some of what we've been building. So, you know, VR is a gamut. It's a whole range. At the one end, we have what I'll call our consumer experiences, right? So this is personal entertainment VR. This is the VR that's been capturing everyone's imagination since we've been talking about it for the last 12, 18, 24 months. Everybody wants to sit at the 50-yard line. Everybody wants to go and be on stage at that concert. These are exciting. These are way fun, and this market is primarily served by NVIDIA's GeForce consumer gaming cards. At the other end of the spectrum, we have what we call professional AR and VR. These are what we think of as enterprise applications. So there's things like content creation, like the movies up there at the left. And one of the reasons that I enjoy being at VRLA is because you guys are the creators. You span sort of both sides of that spectrum. On the one hand, you're using our Quadro line of tools, our professional tools for creating your VR content. And on the other hand, the platform that then is being used for consuming that content obviously is the GeForce side. So on the pro side, in addition to digital content creation, we have a whole range of other applications, right? VR here in Hollywood, we think a lot about entertainment, but you know, you go out and you talk to the medical community and you talk to automotive design and manufacturing, and they are every bit as excited about VR and the potential to really change their workflows as we are here in Hollywood. And VR really is kind of this, it takes a village sort of undertaking. I mentioned GeForce and Quadro. Those are two of our sort of bigger lines of graphics cards, physically larger cards. We also have the Tegra cards, and these Tegra cards are really important as we start to move towards AR, right? Towards mobile applications, whether this is scanning objects or tracking objects in VR, or even presenting the graphics for mobile VR experiences. That's our Tegra line. And I do want to mention our Tesla line, because while most people think about VR as either something that's happening mobile on their perhaps mobile HMD, or something where they're tethered to a computer, there's a whole other side of VR, which is how do we create that content? How do we process those enormous video streams that we want to put together into a 360 video experience, or create something like a light field or photorealistic renderings? All of that content creation is happening in the cloud, and that's being serviced by our Tesla line of products. So I mentioned that it's sort of it takes a village. Another way to put that, I guess, is that it's really kind of a grand challenge problem. And I say that for two reasons. On the one hand, as you know even better than I do, creating VR content is a grand challenge problem. It's really hard. It requires us to rethink all the rules of cinematography. And that is an enormous undertaking. On the other hand, there's the technology aspect of how do we enable a VR experience, and that's what I spend my days thinking about, right? How do we bring together all the technology to bear so that we can do great VR? And I think the world just assumes that we can do it. Right? They've been hearing about VR. They've seen it on the cover of Time magazine. They're just assuming that we're going to deliver. But it's worth taking a look back. And for those of you who did VR 15 or 20 years ago, like I did, it was not a great experience. In fact, it was a horrible experience, and people got nauseous and swore that they would never, ever do VR again. So delivering great VR is not a foregone conclusion. We have just barely gotten there. We have just barely gotten to the point where we can cram enough technology together to deliver a really good VR experience, and it's only going to get better from here. So, so let's pull back the curtain a little bit and talk about what those technologies are that enable VR. So we'll start with the graphics and display. Graphics and display is a really tall order. So on the left-hand side, you have sort of a standard desktop resolution, right? So this would be 1920 by 1080. If I'm interacting with a modeling tool, some sort of pro application, and I'm getting 30 frames per second, I'm super happy, right? That's smooth, that's a great experience. Even if it drops down to 15 frames per second, there's kind of this graceful degradation where I'm not quite as happy as when it was turning smoothly, but it's still okay. I can still do my work. VR isn't like that. VR is kind of this binary experience. If I don't hit 90 frames per second, it is a bad experience. You want to take off the headset, right? And we forget this because we kind of get used to seeing good VR experiences. And then once you go back in the lab with someone who's working on some new content, and maybe they don't hit that 90 frames per second, you notice it very quickly, and you want to exit VR. So 90 frames per second or bust. And now we have to deliver it in stereo. So you can do the math here. It works out that we have to deliver roughly 7 times as many pixels per second. So MPS is megapixels per second, but we have to have roughly 7 times the performance in VR as we do for a typical desktop application. So that's a really tall order. People have been building content that works great in that scenario on the left. How do we now take that content and deliver it in VR and create compelling VR experiences around it? So, so that's the first hurdle, the first bar that we have to clear. The second one has to do with latency. So in VR, an awful lot has to happen in a really short period of time. From the time that I start moving my head, maybe I'm looking in a new direction, maybe I'm just sort of, peering around. From the time that I start moving my head to the time that I deliver a new frame with updated content, I have 20 milliseconds. Right? If I don't hit that 20 millisecond budget, let's say it takes 40 milliseconds or maybe 50 milliseconds, it starts to feel like the world is sort of swimming behind you, and you may not even notice it. At 40 milliseconds, it's not terribly noticeable, but people start to get slightly nauseous, and the more you miss that mark by, the worse it gets. And there are even perceptual psychologists who will tell you that 20 milliseconds actually isn't fast enough, and that part of the reason that people get VR fatigue is the fact that we actually have to do better than that. So let's break down that 20 milliseconds for a second. What has to happen during that period of time? Something has to sense that I've started to move my head. That could be a lighthouse tracker, whatever your particular tracking is. A new frame, a new virtual camera has to be set up, sent down to the CPU. CPU has to create the appropriate matrices, send it down to the GPU. GPU has to start the rendering, complete the rendering, send it to the HMD, and the HMD has to flash the display. Okay, that's a lot of work to happen in 20 milliseconds. So we have a very, very short time budget. And again, if you don't hit that, people get sick in VR. Okay, so how are we able to do it? What's some of the magic behind the technology that NVIDIA has put in place in order to meet these really high performance numbers that we have in front of us? One thing that we're able to do is, in the same way that VR makes life more challenging, it also presents some unique opportunities for how we solve this problem. And one of them has to do with the display. So if you open up a head-mounted display and you look at what the actual displays look like, the images that you're seeing are sort of like that thing there on the left. And the reason that they look like that is that we have to put optics inside of these, the head-mounted displays. And the optics are there to do two things. One is the screen is roughly 2 inches in front of your eyeballs. It's really hard to focus on something that's 2 inches in front of your eyeball, and we don't want that. We want the user to perceive the scene as if it's floating about 6 feet in front of them. So we use the optics to do that. The other thing the optics does is it fills your field of view, right? So you feel immersed in the scene. So in order to create an image that's going to look correct through the optics, we have to pre-warp the image in order to produce the thing that's on the left. So we render the thing that's shown here on the left, then we pre-warp it so that under the optics it looks correct. Okay, so this is where the opportunity comes in. So because we're having to pre-warp this image, we notice that there's a bunch of pixels over here on the side that are not being mapped one for one from this pre-image to the warped image. In other words, there's work that we're doing in here which is getting thrown away as we're moving over to this side. And when you have a 20 millisecond time budget, or when you're trying to hit 90 frames per second, you don't want to do any wasted work. So this is an opportunity, and the way that we take advantage of this is with our previous generation, so our Maxwell generation of GPUs, we introduced something called multi-res shading. And the idea behind multi-res shading was, let's actually render this scene in 9 separate viewports. So let's break up the image into sort of a tic-tac-toe screen, if you will. And this region in the middle, let's render it at full fidelity, full high resolution. But these regions out here on the outside, which are going to get compressed in anyways when I do my warp, let's render them at essentially half resolution, right? So we're not doing wasted work. And the way that this happens is with something called multi-projection. So that was implemented in our Maxwell architecture. Our next generation, our current generation, is called the Pascal generation. So this is on the G4 side, this is the 1070s, 1080s. On the Quadro side, this is the P5000, P6000, P4000. With the Maxwell generation, we further refined this idea of having dense pixels in the middle and sparser pixels on the outside, but now we have a nice linear fall off. So whereas the previous version had discontinuities right here, where this was high resolution and this was half resolution, now with the current generation, Pascal, there's a nice linear fall off as you go from the middle towards the periphery. And we call this lens match shading. Again, it's making use of that same multi-projection architecture, but now it's even a bit more refined. And in the limit, you would have this shape actually perfectly matching the lenses. So putting these together, you get very nice speed up in rendering. The other thing that we've enabled with our Pascal architecture is something called single pass stereo. So before I explain single pass stereo, let's take a look at the traditional graphics pipeline, which is I need to render a left eye image and a right eye image separately, and I do that in 2 passes. So set up the camera, send down the geometry, render, left eye, send down the right eye camera, send down the geometry, render again. In there's some amount of wasted work. And the wasted work is that if I have to tessellate my geometry on the GPU, which we do frequently, commonly now, that's happening twice. It's happening for both left eye and right eye. So the idea with single pass stereo is let's actually send down the left eye and the right eye at the same time, and then just send down the geometry for tessellation once, and then we render it for both left and right eye. And so there's some really nice acceleration that you get if you're geometry bound using single pass stereo. The last acceleration that I want to talk about in terms of graphics acceleration for VR is something we call VRSLI. And here, the concept couldn't be simpler. You have a left eye and you have a right eye for VR. Let's treat them independently. Let's allocate 2 GPUs. One GPU is going to render the left eye, one GPU is going to render the right eye, and then at the very end, just before I send it off to the head-mounted display, I'm going to put those together into a single warped frame. So VRSLI is a great way to get nearly linear speed up in your applications. So, whoops. Okay, there was a graph here, but we'll pretend there's a graph there. What we end up seeing is somewhere between 50 to 80% speed up in applications that are using our acceleration inside of VRWorks. So I apologize that didn't show up there. Okay, so visuals are really important. In fact, that's sort of where we started for VR, was thinking about head-mounted displays, and that's what captured everyone's imagination. But we have other senses, and if what I really want to do is to fool you, to create this grand illusion that you're in some other space, just recreating the visuals isn't quite enough. We rely on audio quite a bit, and so we've created some tools to help accelerate audio inside of VR. So the state of the art inside for VR audio is I have audio sources inside of my scene, and I render them. I create stereo renderings from those sources such that my left ear hears something slightly different from my right ear, depending on the position and direction of where that sound is. Right? So maybe the audio arrives just a split second sooner at my left ear, and maybe it's a little bit louder if the source is on my left-hand side. So that's sort of state of the art, and it's pretty compelling. Like, you can be in a VR experience and you can roughly guess the direction of the sound that's coming to you. Where it falls apart is here. So if I'm trying to create this rich VR experience and I want you to believe that we're in a small elevator, or we're in a beautiful, huge concert hall with great acoustics, just getting the direction correct is not enough. What you need to get in this case is the geometry and the material properties, the audio material properties of that geometry. So in the same way that I can build a model out a scene, and I can accurately predict what the lighting is going to look like, what it's going to look like visually, and I do that through path tracing. I have virtual photons that sort of move through the scene, and I get out a photorealistic image. I also want an acoustically realistic image. And in order to do that, we can use our same exact machinery that we've built. Specifically, we have something called our optics ray tracing engine that we use for making the visuals. And now we've hijacked that, and we're repurposing it for creating audio. And with this, you can get fantastic, very compelling audio experiences where you can tell the difference between I'm in a long hallway or I'm in a large open space, like this room. So audio is super important, and we've made some great strides. The next one that's worth mentioning is touch or physics. So right now, for most of our VR experiences, the best that we get in terms of haptics feedback is some rumbling, and that's actually pretty good. Like, it helps a lot with many VR experiences to get that sort of tactile feedback. We're looking forward to that moving much further. So NVIDIA's role in helping to create great haptics is not that we're building haptic feedback devices. That's not really what we do. Instead, we're building accelerators. So the main problem that you have to solve if you want to introduce haptics into your VR scene, the first one is the collision problem. I need to be able to identify very precisely when one object comes in contact with another object. Right? If I'm going to touch something, you got to get that right. The second part is when that object comes in contact with the first object, I need to solve some physics problems to figure out, does one of them deform? How do they respond to each other? And it turns out that because NVIDIA has been in the market of making great video game accelerators for a long time, we've been able to repurpose all of that technology into our VRWorks SDK. Right? So in the same way that in your game, you need to know when two objects collide and they have to do the right thing, we've now hijacked that and are using that for many of our VR applications as well, and now we've exposed that for everybody else to use. The other part where physics is really useful is VR should not be a static experience. Right? We want our VR to be dynamic. And again, we have a lot of experience with games where they also have to be wonderfully dynamic. And so we've repurposed things like PhysX and Flex so that we can have water simulations Or in the case of VR Funhouse, we can simulate goo coming out of a squirt gun and have it accurately modeled. Fire spreads realistically. Our HairWorks SDK is fantastic for producing furry creatures inside of VR. So all of these are really important as we want the objects in our scenes to start behaving realistically and have the physics be very plausible. And as I just mentioned, our VR Funhouse game, who's played VR Funhouse? Excellent. So VR Funhouse, in some sense, is a proof of concept where we rolled up all of this great technology that we had put together into VRWorks and showed how it could all be merged into this great, super fun game. So if you haven't played VR Funhouse, I highly recommend that you go get it. It's free. You can get it on Steam Store, Oculus. It's way fun. It has a bunch of mini games inside of it, and they're all using NVIDIA's acceleration and physics underneath it. So great experience. I highly recommend that you get it. And if you're a creator, you may even have more motivation to go get it because we've open sourced this. So if you go and you play VR Funhouse, and you're like, wow, that's really cool. I like the way that the plates shatter, when I shoot them, or I like the way that the green goo comes out of that gun. I'd really like to put that in the experience that I'm creating. That's really easy, because now you can go look at the source code. You can look at the UE4 blueprints and copy and paste and put those into your own applications. So we've opened this wide open. You can go download it from GitHub, and I encourage you to do that. The last key technology that I want to talk about is capture. So most of what I've been talking about to this point has been about rendering, about synthetically recreating an environment that's going to fool us. But there's another part of this, which is there's great content all around me, and there's some really great examples on the expo floor where people have built beautiful rigs for capturing reality. Right? Either sort of 360 capture all around you, or rigs where from a single point you're looking in all directions, so inside out, outside in. This is all fantastic data. But it leads to a really difficult computational problem, which is how do I take all of that data from all of those cameras and put it into a single unified scene? So how do I stitch together video from a rig like this, which is a really great capture rig, and put them together? So why is that hard? It's hard because the cameras are not calibrated to each other, right? So each one has slightly different parameters associated with it. Figuring out how to do the blending across cameras is actually really hard. And so in order to help people do this, in order to help people put together the output from these fabulous rigs, we've created something called our 360 Video SDK. And it's as simple as it sounds. So you point it at these video streams. It then goes through the difficult computational problem of putting them all together into a single unified video format, and then outputting it. And it can work in two modes. You can either run it in real-time online mode, or you can run it as sort of an offline processing of your video. So this is also part of VRWorks. It's been sort of pre-announced and will soon be available for you to download. So I touched on a number of these components. For completeness, I decided to put up this image that shows all of the pieces of the VRWorks SDK. If you're a headset manufacturer, maybe you care about these things in the middle. For the things that you probably care about as a content creator, we've kind of hit many of the high points in here. And if you happen to be developing on a game engine, like the Funhouse application that I was just showing you the screenshot of, really good news. You don't have to worry about the underlying details of VRWorks. We've already gone through and integrated it for you into Unreal Engine. So if you're working with version 4.12, 4.13, 14, 15, all of those are available in the NVIDIA branch, which I've put the URL here. So our branch basically has the standard build, say of 4.13, plus our technology, our VRWorks technology integrated. So that's freely available. You have to have a GitHub account, but you can go and download it. And as mentioned, I don't know how legible that is, all of the graphics features that I just mentioned, multi-res shading, lens match shading, single pass stereo, VR SLI, those are all integrated and available, and there's really great tutorials for how to access them. Similarly, if you're developing in Unity, this is coming soon for you. So really soon. So all of this technology, same technology, will be supported in the mainline version of Unity. So all you have to do then is download the VRWorks plugin, and it all just works. Right? And again, there are great tutorials that will show you exactly what you have to do inside of your Unity application. And without very much effort at all, you'll see 50, 60, 70% speed ups in your application. And again, when we're talking about VR, the difference between 70 frames per second and 90 frames per second is a really big deal. So if you can get all this speed up for free, just by downloading and enabling this package and writing a few lines of code, that's huge. So I highly encourage you to do that. The last thing that I want to talk about is profiling. So VR is really hard to profile. You've got 90 frames per second, roughly, of stuff going on. It's largely opaque, and it's hard to know where between the CPU and the GPU are things slowing down. If I'm not hitting that 90 frames per second, why? And so we have a tool, a suite of tools that we've developed called Nsight. Nsight is great. It plugs directly into Visual Studio, and it gives you a ton of information about where your time is being spent within the rendering of each frame. So you can use this to profile, to better understand your code, and hopefully then to go in and fix bottlenecks and speed everything up. Okay, so I think we've touched on most of this, but just to recap a little bit, traditionally when people think about NVIDIA, they think about this bit over here, the hardware piece. And don't get me wrong, this is a really important piece. Without that part, we really can't do the rest of it. But especially for something like VR, it's not really quite enough, right? It wouldn't matter if we had all the great VR goodness in the world. If we didn't expose it, if we didn't make it easily accessible to you, it doesn't do anyone any good. So we've taken this, and on top of our cards, we've layered our SDK. I talked a little bit about Nsight and PhysX and more about kind of the whole VRWorks framework. So this is all freely available. A lot of it is encapsulated in the driver and then exposed through VRWorks. And more we're building applications. Oftentimes because the applications are fun, but also so that we can provide you with examples that show you how to take advantage of our SDKs and our underlying hardware. So it's really a platform, a complete end-to-end platform. All right, so one final word. Every year, NVIDIA has our GPU Technology Conference. This is sort of our big event. This is happening next month. So this is May 8th through 11th, just up the road in San Jose. If you haven't been before, I highly encourage you to check it out. Every year, for the past couple of years, we've been adding more and more VR content. We have over 30 hours of VR sessions this coming year. Tons of cool content from great speakers spanning industry, academia, national labs. So great lineup of speakers, really cool experiences out on the exhibition floor. We'll be showing some never before seen NVIDIA experiences in technology. We also have a great lineup of partner experiences. We have something called the Content Showcase, where I know some of you applied to and are part of that. We're highlighting early stage startup companies that have created really cool VR content that we want to help them promote. If you didn't enter this year, I encourage you to enter next year. It's a great event. This year, we're giving away $30,000 of cash to the winner. So really exciting, fun event. So if you haven't been to GTC before, highly encourage you to check it out. If you have been before, please come back. We have new, exciting content this year. It's going to be a great event. Okay, I think that's my final slide. I left a few minutes here. Happy to take any questions that you might have. I can half hear you. Can you come closer? Or use the microphone?
I've got a mic. Is FCAT built into the Nsight tool set?
No, I think, so that's a really good point. So FCAT is a great frame profiling tool. At this point, I believe that it's independent. You can go and download it separately, and it's also a really good way for profiling your VR applications, but I don't think that it's wrapped up with Nsight. I think there's another question. These lights are really bright.
Hi, and thank you for an informative presentation. I had a question about the tools that are available through Unreal Engine and eventually Unity. Do
Yep.
they include the audio?
I don't think that has been wrapped up yet. I think that's a coming soon sort of feature. It's when we first started implementing the 360 audio library, the original target for it was acoustic engineers, right? We wanted to build something that was going to be super, super accurate. And of course, to do that was going to require a fair amount of hardware. And so we have trimmed that down. So it's, in order to make it work with a game engine, we have trimmed down the implementation. And I know that the expectation is that we will make it work integrated with the game engines, but it is not yet available with them.
The only way to use it would be through the SDK directly?
That's correct. Yep. Any other questions? All right, then we'll wrap up early. Great. Thank you very much, everyone.